All right, guys, so what we're looking at here is this is the review for the Solids of Revolution test. Now, the one thing that is true about this review, more than any of the other reviews, is as we go through the slides, all of the work will already be done as far as the setup goes, and the answers will not be, like, they have not actually been calculated. In other words, I didn't type any of these into my calculator, because I figure, if anything, you guys can do that on your own. So just be aware that the setup will be here. Typing them into your calculator is kind of up to you to get the correct answers, okay? So on numbers, so here we go. Let's just dive right in. On number 1, what we're doing, notice it says that we're finding the given area. Now, when we're finding area, if you remember, it's the integral from a to b of the function that is on top minus the function that is on bottom. This is unique to area because when we do, like, when we revolve things around an axis, it's always the furthest axis minus the closest axis. In these problems, it's always the function that's furthest from the x, or the function that's on top, minus the function that's on the bottom. So on number 1, we do have to find out where they cross. So when I graph these, like, you get 1 over x squared looks like this. Y equals x looks like this. They cross right here at x equals 1. And then it has x equals 2 as the second line that we're going to have. So this area right in here is what we're looking for. Okay, so that's why we do the integral from 1 to 2. X is on top. 1 divided by x squared is on the bottom. That is how we find that area right there. And again, you just type that right into your calculator and find out what that area is. On number 2, very similar. Like, I look at sine of 2x, or sine of x looks like that. 2x looks like this. Pi fourths is actually right here. So this is looking for this little area right here from 0 to pi fourths. 2x is on top, sine of x is on the bottom. You just type that into your calculator. One thing that will let you know if you've done something wrong, if you've gotten the order wrong, like top and bottom, is you'll get a negative answer. On this entire test, there is no way that you can get negative answers because you're either looking for area or you're looking for volume. Both of those are positive numbers just in general. So that's how we find it on numbers 1 and 2. I'm actually going to have you skip number 4 because it's more difficult than it's intended to be, and there's not a picture that goes along with it. So don't worry about doing number 4. On number 3, if you were to get the y by itself, you would divide by 2 and then take the square root, okay? And you would get this particular graph right here. So you'd have that piece of the graph. And you'll notice that in order to do this problem, we're looking for this area. Now, technically, you could have done it another way as well, and it would have been fine, and it would have given you the same area either way. But I found on this one it's easier, since the x is already by itself, to find this area by just doing, again, we did right minus left. In this case, the right function is 2y squared. There is no left function because it's just the area between this function and the y-axis. So we do the integral from y equals 0 to y equals 3 of 2y squared dy. Don't forget, when you type that into your calculator, you can just use x's and you're totally fine for finding that area. On number 5, you'll notice that we're starting to revolve around the x-axis. Now on this one, we're going from x equals negative 1, so x equals negative 1 is right there, to x equals positive 1 right there. And again, that's not drawn exactly right. But 3x to the 4th more or less looks like that. We're going to revolve that. Remember, that's pi times the integral from a to b, so we're going from negative 1 to positive 1. In this case, we have the disk method because there's only one function. We don't have two different functions that are enclosing an area. We're talking about the area that exists between that graph and the x-axis. So that's why we're using the disk method here, why there's only one function, and we would just take that function and square it because that is our radius as we revolve it around that axis. On number 6, it's pretty much the same thing. If I graph 2 plus x cosine of x from negative 2 to 2, I don't have a picture of the graph, but because it's the x-axis that is enclosing it from negative 2 to positive 2, and I can't remember exactly what it looks like, something like that, not even close really, but this is what we are revolving around the x-axis. So I'm squaring that entire function, pi's on the outside from negative 2 to positive 2, just type that right in. Again, another disk method problem. Same on number 7. The only difference here is the interval is written a little bit differently. So you're going from 0 to pi halves. Doesn't change how you do anything. Again, the one thing that I see a lot of people miss when they do these problems is they forget the pi that goes on the outside. Now on number 8, finally, number 8's a little weird because we're revolving around the y-axis. So we're revolving around this axis right here. So I look at the graph and I'm saying, okay, I've got y equals x squared plus 1, then I've got y equals 5 and x equals 3. Well, x equals 3 is this straight line right here. If I wanted to find out where those two graphs cross each other, what I would do, and I actually think I have that, so I want to find out where they cross. The way that I find that is, and again, this is, I can see that I did it incorrectly. I take 3 and I plug it in, so I get 3 squared plus 1 is, for my x value, what did I do wrong here? Okay, so I can see what I did wrong. I actually have the wrong enclosed area. So I've got my graph, looks like that, and I've got y equals 5 right there. And then if x equals 3, that's actually further over here. X equals 3 is right here. So the area that I'm looking at is right in here. Now, I'm going to start, and I'm revolving that around the y-axis. So everything has to be in terms of y. Well, when I look at this, and again, this is wrong altogether. I just need to reset this up. When I look at this, I'm starting at y equals 5, and I'm actually going up. The way that I find out what I go up to is I take the x value and I plug it in, and I'm going all the way up to 10. So I'm going from 5 to 10. Then I'm doing, because we're revolving around the y-axis, we're doing the function that's further away, that's x equals 3. So I go 3 squared, there's a pi out in front, minus, and then I have to get the y, or the x all by itself here. So that's going to be x equals the square root of y minus 1. So I'm going to go square root of y minus 1 squared, and then I've got dy on the end. And again, I apologize, that was set up wrong initially. This is how you would set that problem up because this is the area that we are revolving around the y-axis. On number 9, again, we're revolving around the line y equals negative 1. Y equals negative 1. This one we can actually draw. Y equals the square root of x looks like this. Y equals 2 is up here. So I would find out that I'm going from x equals 0, then those two graphs cross at x equals 4. So I'm doing the integral from 0 to 4 of pi times, we're revolving around this line down here, y equals negative 1. So the function that's further away is 2, so I'd go 2 minus negative 1, that's the same as plus 1, minus the square root of x minus negative 1, again plus 1, and then we square both of those. Type that into your calculator and that will tell you the volume that is generated by revolving this shape around the line y equals negative 1. On number 10, we're going around the line y equals negative 2. Okay, so when we think about this, I've got y equals x squared, that looks like this. Y equals negative x plus 2 ends up looking like that. And, I mean, the graph's not exactly right, but that's what that looks like. And I find out that that goes from x equals negative 1 to x equals positive 2. I'm revolving that around this line down here. So I'm revolving around y equals negative 2. You'll notice that negative x plus 2 is further away in the area that we're talking about, so that's why we put that one first. Minus negative 2 gives us plus 2 squared, and we do the same thing with the second function. So that's how we do number 10. Number 11, we're going around the line x equals 3. In order to see this one, we have to graph it. So I've got y equals x squared, y equals 1, and x equals 2. So we're looking at this area right in here that we're going to revolve around this line x equals 3. On this one, actually, I did this on purpose to show you, technically, if you go the square root of y, because that's further away, this is y equals x squared, but you've got to get the x by itself. So if I get the x by itself, I get x equals the square root of y. That is the function that's furthest away. But notice what I did here is I went the square root of y minus 3. If you accidentally flip-flop them, because really it should be 3 minus the square root of y, it actually doesn't matter, and that will give you the correct answer. So really on this problem, I could go the integral from 1 to 4 of 3 minus the square root of y squared minus 3 minus 2 squared. Either one of those answers will give you the identical answer, and in reality it doesn't matter, and you're good to go. So that's number 11. Number 12, kind of the same thing. We've got to get the x by itself, so we take the cube root of both sides. This is the area that we're revolving around that line x equals negative 2. So I've got x equals 2, 2 minus negative 2 is plus 2. You can see it here. Type that into your calculator and you're good to go. Again, kind of the hard part here was realizing how to get the x by itself by taking the cube root of y. 13 through 16, we've got that graph up in the corner and you can see that and you're like, okay, we're going to do a bunch of different things with it. First of all, we're going to rotate it around the x-axis. So in order to do that, I do have to find out what y is equal to. So I get y is equal to the square root of 4x. We take that and we put that in as our function that's further away from the axis that we're revolving around squared, minus x squared. You notice as well we're going from x equals 0 to x equals 4 because that is where the two graphs, that's not actually, yes it is, they cross at x equals 4. Strangely enough, the point where they cross, both the x value and the y value are 4, so they cross at the point 4, 4 right there. So on number 15, even though we're going around the y-axis this time, what you're going to do is we're going to do, 14, sorry. On number 14, we're going around the y-axis, so I've got y squared because that's further away from, oops, I've got y, that's y equals x, x equals y. That's further away from the axis we're revolving around, minus, I did have to divide by 4 to get the x by itself, so x equals y squared divided by 4. So that is furthest minus closest, both of them are squared. You'll notice on 15 and 16 what we had to do, because we're revolving around different lines now. When I revolve around the line x equals 4, that's that line right there. So we're revolving around that. That's why I've got 4 minus, oops, x equals, yeah, that's right, 4 minus y squared divided by 4. You can see all the answers there. All of those are correct. See if you can figure out where those came from in order to truly understand how to do these problems. If you don't, you can definitely ask questions about where I got any of those. But the setup on all of those is correct. Now on 17 and 18, what we're doing is we're going back to cross sections. If you remember, the way that we find the volume generated by a cross-section, which was your art project, is you do the integral from a to b of the area of the cross-sectional shape times by dx. So on the first problem, it does say that we're on both of these actually, we're going from 0 to pi. So I know that that's why it's from 0 to pi. On a semicircular disk, we're going from 0 to pi of 1/2 times pi r squared. And then we have dx on the end. Now I've drawn a picture here. As we find out how far it is from there to halfway through, what we're doing is we're finding the radius, the distance between sine of x and negative sine of x. So all the way down would be sine of x minus negative sine of x. That's where the sine of x plus sine of x is coming from in number 17. Because 2 minuses make a positive, then we have to cut it in half to find the radius. So that's how you set up number 17. On number 18, because they are squares, we're going to do the integral from 0 to pi of the base squared times dx. So on this one, what's happening is I've got sine of x, I've got negative sine of x, looks like that, and then the squares are coming off of the paper, very similar to what you did in your art project. Just like that. We square all of them, we put a dx at the end, we do from 0 to pi. Couple of things to note here. There is no pi on the outside naturally in these problems because we're not revolving around the x-axis. On number 19, it's a little bit different because it tells us the base is running from one function to the other function. If you were looking at this, we've looked at this graph quite a few times. I've got x squared like that, I've got square root of x looks like that. So this is the area that we're using, but it tells us whatever the shape is this time, the area is 2/3 times that base squared. Well, the base just runs from the square root of x to x squared, so we subtract them. So you get the integral from 0 to 1 of 2/3 times the square root of x minus x squared. Then the whole thing is being squared due to the fact that we know that the formula for the area is right there. Okay, so again, that's cross sections. Hopefully that one kind of made sense as well. 20 through 25, they're all limit problems. Okay, so what we have to do, and number 20, I'm not like a huge fan of. I probably made it a little too difficult. When I plug 0 in, I get 0 minus 0 over 0. So I get 0 over 0, that's the indeterminate form. So then I have to take the derivative. When I take the derivative of this, what I get is 1 minus 1 over 1 plus 2t times 2. So when I take 0 and I plug it in, I get 1 minus 2 over 0. That is, the limit does not exist. Okay. The other problems that you have, notice on number 22, I do want to call your attention to number 22, that you have to use the product rule to take the derivative between x and the sine of x. 23, 24, and 25, technically we could use, 23 and 24, we can use the limits as x approaches infinity. 25, you just got to be careful. when you take that derivative to make sure that you get rid of the 18 and the 36 when you take the derivative. Anyway, hopefully those all made sense. Check your answers here. 22 does take a little bit of time because you have to use L'Hopital's rules twice. But if you have any other questions about that or anything else, please let me know.